Containers are the foundation for how modern business-critical apps are built, running across Kubernetes environments and multiple clouds. These are high-value targets for attackers, who are now using AI to accelerate ways to find and exploit vulnerabilities faster than humanly possible, from code to runtime. And it's hard to respond effectively when security signals and responsibilities are fragmented across different teams and tools. The challenge isn't just finding security issues, it's understanding how they connect across the lifecycle from development to production. So rather than treating supply chain and runtime as separate problems, Microsoft Defender for Cloud brings them together into a single unified model to catch issues early in code by identifying vulnerabilities and misconfigurations, prioritizing risk across clusters, workloads, and configurations, and detecting and responding to threats in your running containers in near real time, all while tracing them back to the source to put the right mitigations in place. So let me walk you through a multi-stage attack across a containerized environment to show you this in action from the perspective of a SOC analyst. I'm in Microsoft Defender in the incidents view, filtered to container-related incidents, and I can see 4 related to containers. Let's start with this one, a multi-stage incident involving multiple users. And notice this is already correlated into a single incident, not multiple alerts. You can see it's flagged as high impact with a critical asset label, and the crown icon in the incident graph showing asset criticality. On the left is the attack story with alerts listed in chronological order, color-coded by severity. If we go back to the incident graph, container resources are in black, and related identities and services are in white. This is runtime threat detection correlated across layers. In this case, Defender has detected 19 alerts for this incident in near real time and stitched them into a single timeline. So let's walk through the attack. Here we can see the initial access signal was from a Kubernetes API request from a proxy IP address. Identity compromise and escalation then occurred with credentials accessed from a service principal. And finally, Defender for Cloud's cross-cloud correlation surfaces lateral movements spanning environments, revealing a brute force attack originating from an exposed Azure Kubernetes cluster targeting an AWS relational database service resource. Back in the graph, you'll notice a blue icon. This indicates there are related attack paths. And if we ungroup similar nodes, we see a user indicated by another blue icon, and we can pivot directly into the attack path view. Here's where it gets interesting. This is where we connect runtime activity back to security posture and exposure. It's concluded that the container is internet exposed with high severity vulnerabilities, and it's using a managed identity to access a protected storage account. We'll come back to this in a moment to see if we can fix the root cause. So we can see this wasn't just an isolated runtime event. There was a clear path from exposure to exploitation. So let's move on to the second incident in our queue. This is another multi-stage attack, this time focused on initial access and discovery across multiple endpoints. In the incident graph, we can see a number of containers were accessed. Then in the attack story, we can see they were hijacked to be used as crypto coin miners. Now, containers should be immutable, only running what was in the original image. But this alert shows the initial binary drift. This signals to Defender that the container is executing something it was never built to run. And if we review the activities for this alert, we can see a suspicious parent process and a shim file being used to execute it. And if we move to the right in evidence, we can see all the details for the process, file, pod, and cluster. This is where runtime detection becomes critical, because this activity isn't visible through image scanning or posture alone. From here, we can investigate and build full context around the attack. For that, let's drill into our Kubernetes cluster and start hunting to take a look at the processes run across both control plane and data plane signals. There are tables that log these events for querying, CloudProcessEvents for runtime activity, and CloudAuditEvents for control plane actions. Let's run a query in the audit events table to search for the creation of a cluster admin role binding. This would grant full administrative access to the cluster. Here we can see the role binding and associated subject, and it confirms our assumption that the privileged escalation did happen. Next, we can leverage Security Copilot to transition from investigation to response, using guided recommendations informed by the attack insights uncovered. Here, Copilot has already generated an incident report, At the top, we have a summary of the attack from correlated signals. If we expand it, under credential access, we see compromised identity activity. Under discovery, there are network scanning tools. Under execution, we see confirmation that the container was modified to run crypto mining processes. And below that, the triage section then lets you classify the incident as true positive, informational, or false positive with corresponding subcategories. I'll choose a true positive multi-stage attack. Copilot also suggests 2 remediation actions: terminate the pod to stop activity, or isolate the pod to contain the threat. So let's follow that guidance and isolate the pod. So I'll close Copilot and return to our incident graph, then ungroup similar nodes again. Now selecting the pod, under Actions, I can isolate the pod. I'll add a reason, and then I just need to confirm. And just like that, we've moved from detection to investigation and containment in a single flow. So far, we've focused on detecting and responding to active threats, but security doesn't start at runtime. And this is where Defender for Cloud helps your DevOps teams harden your environment to prevent issues from reaching production in the first place. Using policies, you can put rules in place to prevent containers with issues from being deployed. So for that, in the Azure portal in Defender for Cloud, under Environment Settings, we'll head over to our security rules. Here, we've already created a handful of rules to deny or audit activities. For example, if I take a look at this one to block vulnerable deployments of AI applications, this rule is configured to automatically deny deployment of any image violating the policy. It's scoped specifically to the namespace of our AI applications. In the Configurations tab, we can see that this rule is set to trigger when a container image contains a high or critical severity vulnerability, with any count higher than 0. With our policy in place, let's test it out by attempting to deploy a container image that contains a few high severity vulnerabilities. This is exactly what happens with supply chain attacks. For that, from Cloud Shell, I'll run an AKS command first to get my credentials. Now I can execute my command. I'll paste in this kube control command to run an image, including its location and namespace details. And immediately, we can see that the run was denied, stating that the image contains 415 CVEs, and we allow 0 in our policy, so it's blocked. What's more, Defender for Cloud continuously scans what's in your registries and running environments in near real time, surfacing the risks that matter and turning them into clear, actionable fixes. Next, over in Recommendations, we can see findings identified by Defender for Cloud with several critical risks highlighted, related to the same incident that we saw earlier in the Defender portal. And these are its recommendations. Let's look at this one to update BusyBox. Looks like this version has 13 known vulnerabilities. And digging into the Remediation Insights tab, we can see more details across the development phases. The Take Action button tells us to assign an owner and to create a GitHub issue. I can create the GitHub issue from here, and if I head over to what our dev team would see in GitHub, you can see the details for the ticket with deployment info, matching CVEs for this version, and below there are remediation guidelines to mitigate the issue. From there, we can assign the issue to GitHub Copilot, and the GitHub Copilot coding agent will generate a draft pull request fixing the CVEs for review. Once the pull request is actioned and complete and the version is updated, we can see that the CVEs were resolved. And finally, as a developer, we can merge the pull request to get our app back into a healthy state. And when I return back to Microsoft Defender and our app recommendation, clicking on the GitHub issues shows that everything was resolved and it sent the updated status back to Defender where your SOC lives. So that's a hands-on look at how Microsoft Defender helps secure your container environments end-to-end. It doesn't just detect security issues, it helps you respond faster by connecting security signals across the entire lifecycle, from development through production. To learn more or get started, visit ak.ms/Defender Cloud Security. Be sure to subscribe to Microsoft Mechanics for the latest tech updates, and thanks for watching.